Welcome to this video about fundamental object orientation. In this video we will talk a lot about different types of models. My name is Tobias Olsson and this work is licensed under the Creative Commons Attribution Share Alike. It describes some phenomena in real life and it's very fit for the purpose of understanding how things move in the world that we usually occupy. However, the classical mechanics does not work in every situation. For example, if the speed of things becomes very large, we need to use another model, relativistic mechanics. Or if the size of things becomes really small, we need to use quantum mechanics. So models are something that describes something in real life, but as real life is very detailed, the model makes some simplifications. It also makes some assumptions that the classical mechanics makes the assumption that we are moving in normal speeds and have normal sizes of things. So it's important that you use the model and you know the assumptions of this model, because otherwise you risk making mistakes. So basically models are something that describes real life, that can make predictions in real life in a specific situation, and it makes assumptions and simplifications. In software we also use models. We use models for specification, that is describing the requirements of the system. We use models when we develop. For example, the models that we have looked at so far is basically for development. We have looked at the class diagram model and we have looked at the sequence diagram models. We can also use models for verification, and that is testing out that our system behaves as it should, as specified maybe. In software systems, models can be mathematical, that is formal models. This is a whole area of itself, so this is nothing that we will talk about in this course. Basically, it's about mathematically proving that the system actually does what it should. Very exciting stuff, but not part of the course. We will look more at these informal models that we can use for aiding in communication between stakeholders, for example, between developers, so that two developers can have the same understanding of how the system should work at a certain level. These informal models can be visual, as we have seen in this course so far, but more importantly, they are also mental. So you get a picture of the model in your head, so to speak. And this is something you always do when trying to understand something. You create this mental model. A visual model on a paper is something that you can use, of course, to remember this model and remember, okay, this is the way I thought about this part of the system, or communicate this to someone else. When talking about visual models, you can have more of a blueprint style, that is a pretty exact specification of how things are done. This is more or less what we have seen until now. It's very detailed. It almost is exactly the same as the implementation. And you can have more sketch style visual models that are maybe the most common, that you draw some boxes on a whiteboard or a piece of paper, you discuss with your peers and you come to some form of conclusion based on this. Maybe the sketches are even thrown away later. We can make visual models at a very low level, some very little small detail of a system. In our case, we have more or less made a pretty detailed blueprint over the whole system, as this system is very small. As you probably understand, we cannot have this level of detail for an entire system with maybe hundreds or thousands of classes. It would be impossible to look at. And you can have these visual models at a high level, maybe describing the major components, the major modules, or the most important classes in the system and how they are connected. This can give an overview or a high-level understanding of how things are actually working. This is probably what you could encounter in real life. As I've already mentioned, these visual models are often divided into static and dynamic models. So static models, time does not exist really. You just show a snapshot of how things are. Dynamic models, on the other side, show some kind of time flow, a sequence of events, or something like that. You can look at the structure. Typically, you have static models for looking at the structure of things. How are things connected? Or you can look at the behavior of things. And typically, you use dynamic models for looking at behavior, how things are actually executed. So it's important also here to realize that source code and systems are also models. We make assumptions and simplifications when we create a system. And this is reflected both in the actual executing system and in the source code itself. The source code itself relies on some assumptions of how it's compiled or interpreted by an interpreter and then executed on a CPU. These software models that we create can be coded. This is basically what we are doing. We are hand coding these models into source code and then executing them. Software models can also be learned. So, for example, image recognition is very hard to hand code. Recognizing characters or cats or faces is super duper hard to hand code a model for this. Instead, we train these models using a lot of examples. Typically, this is what we call AI or machine learning. Systems also have an effect in real life. People make decisions based on systems, what they say. People's lives are affected by systems, so it's something that has an effect in real life. So maybe this sounds very strange right now, but we will take a look at Facebook as an example. The basic model of Facebook is a model of a social network. So the model facilitates communication between the nodes in this network, and basically you can think of this as a graph. The humans are the nodes and the edges are the paths of communication. So friends are connected to friends, and using these connections they can communicate and see what people are up to. This is of course a simplification of how humans normally communicate. You cannot express the full range of human emotion using Facebook. For example, the reactions you can have on a post in Facebook is very, very simplified, and misunderstandings are quite common. If you post the emoji icon, what is actually meant it's very hard to know. If you post the heart icon, what do you actually mean? It's a common source of misunderstandings. So the Facebook model of a social network relies on some assumptions. The basic assumptions is that humans are well educated, well informed, and nice. Thus, the idea is that the important and nice information will fill this network. Maybe this is actually an assumption that is not working out that well in real life. Another assumption you can say that the Facebook relies on is that social pressure should make sure that people behave well towards each other. This is also maybe something that we can debate if these two assumptions actually hold well for social networks and social media in general. We have seen a flood of fake news. People get into arguments over misunderstandings, maybe because of these simplifications and things like that. So we can see that the Facebook social network is a model. it relies on some simplifications and it makes some assumptions of how things work, and it has an effect on people's lives in reality. So the system is a model. The implementation that you make, that you create as a programmer, is also a model. And this is maybe the most detailed model because it will later be converted into the final system model by a compiler or by an interpreter. And by doing that, you also make some assumptions that this compiler or interpreter works in certain ways when you create your source code. The implementation model, the source code, is the only model that's always needed. This is what we do to create the final system and what's actually executed. While it's needed, it's very detailed. So the implementation model is of course very detailed and often quite large. And this makes it hard to reason about certain aspects of the implementation. For example, is it easy to know what parts can be reused by looking at the source code? Maybe not, especially if the source code is large. Can we decide what parts will be affected by a certain type of change? Not that easy by just looking at the source code. And similarly, it's hard to know what parts are hard to test. Can be hard to know how we should divide work between us. How shall we facilitate change? What parts will need changing or simplification to make it easier to change them? What parts will need to adapt if there is a change in our requirements or in the environment? For example, maybe we want to change the operating system of our system, or maybe we want to change the graphical user interface to some other type of platform. Just looking at the source code can be tricky to know what parts will need to adapt. And how can new developers really understand how things are to work? So introducing a new developer to a system can be a daunting task and take quite a lot of time, especially if this developer has no overview of how the system works or can know where to begin to try to understand this system. Just giving the source code as a big blob of files is probably not the most efficient way. So while the implementation model is the only model that is actually needed and in some respect contains the truth of the system, we also want to complement this by using other types of models. And basically we have looked at almost all of these models already. The first model is the class model, and as I've said before, this model shows a static view of the classes of the system and the subsystems. In a static model, time does not exist. So there is no notion of time here. So we can use the class diagram for analysis, as we saw in the little dice game, and in design, and quite detailed design also. To visualize the class model, we use UML class diagrams, and basically these are little boxes with lines between them. And we can show how the classes relate to each other. Remembering the dice game, we know that the dice game itself contained two dices, D1 and D2, and we show this visually by using this arrow here, and also actually the name of the implementing attribute, the role name we call it in a class diagram. And this arrow is called an association. And this shows that the dice game has an association to the dice called D1. This also shows that the dice game in some respect knows about the dice, and also that the dice does not know about the dice game. And this is an important distinction, and this is what this arrow actually means here. So the dice game knows about dice, dice does not know about dice game. We also saw that the player actually used the dice game, sent the play message to it, and it used this dice game by getting an object as an argument to this have fun operation. And inside of that operation, it used the dice game to send the message play to it. And we show so that there is no association in player to the dice game. Rather, it's this other type of arrow, and this arrow is called a dependency. And it means that player knows about dice game, but it's not an attribute of the player. So it's not an association. Basically, it's this thing, this argument here that makes the dependency. And consequently, player knows about dice game, but dice game does not know about player, and hence it's this directional relationship. Knowing what the different classes depend upon, we can extend our reasoning, and this visual model makes it quite easy to see that, okay, if I want to reuse the dice game, then I also need to reuse the dice. If I want to reuse the player, I will need to reuse the dice game and the dice. So this makes it harder to reuse the player compared, for example, to reuse the dice, which does not depend on anything. So this one we can just take as it is, while this one we also need to take the dice. So if we want to reuse the dice game, we need to also reuse the dice. We can easily see that we could have three programmers here. One programmer implements the dice, another one implements the dice game, and the third one implements the player class. Also, we know that if we change something in dice, this may have an impact on dice game. So, for example, if we change this value to be 1 to 16, maybe the rule here that we implemented in play will not work as well as it did before. So we know that if we change dice, the things that depend on dice may also be affected. And consequently, if we change dice game, maybe player is also affected. So in this way, we can judge the impact of a change, the maintenance and change effort. So if we have a class that we have a lot of dependencies to, changing that class is often a little bit risky, because we need to check that something does not become broken in all of the other classes around it. So let's take a look at how the class model is connected to the implementation model. As I've said before, we of course have the declaration of the class that corresponds to the class name. If we have associations, we implement these as fields or member variables, or what you call them in your particular language. And of course, we implement the operations also. So in this way, we know that we should have an operation called play, returning a Boolean value, and inside of this there should be some kind of implementation. And as I also said, this relationship here, the dependency relationship, can be caused by having, for example, an argument to an operation that uses an object. So in this case, when we send the message "have fun," we supply the player with a dice game, and the player can later then use this in this operation. The next model we will look at is an object model. As it's an object model, it's something that is actually shows something about the system when it executes, because objects exist when we execute the system. In this case, we will take a look at the sequence diagram, and you have seen this sequence diagram before also. So the sequence diagram is a dynamic view over what happens in some scenario. A scenario is a specific situation where more or less specific steps happen. And it shows how the objects behave over the time to realize, to fulfill the scenario. So the scenario describes more in text what should happen in different steps, and the objects change their state depending on what happens, and sends messages to other objects. You can see a little bit of an example of quite a high level sequence diagram from the Home Assistant API documentation, where you have three objects: user, client, and the Home Assistant object. And time flows downwards in such diagrams, because first you log into Home Assistant, the client response with a URL, and then the user goes to this URL and authorizes, and so on and so forth. So using the sequence diagram, we can reason about key aspects of how the system operates. So we can try to understand how some high-level functionality actually works in the system, what parts are involved. We can see how specific features are to be implemented, and we can reason about qualities such as performance and security. So we can take a look at the sequence diagram and maybe spot parts that will, oh, this will probably not perform that well because we have many calls to perform this simple task, or this is done in a loop, so it's quite time consuming. One important aspect of the sequence diagrams are that they are quite a good starting point for class model design. So you start with actually having a specific scenario, and then you create a sequence diagram showing what objects are involved. And based on this, you then create your class diagram. Another way is to do it in reverse, where you first create the class diagram and then test drive this class diagram with a sequence diagram in some scenario and see that, well, this seems to actually work as intended. So we have a connection of models again, the sequence diagram and the implementation in this case. So remembering back to our dice game, we know that we have two dice objects. And these two objects are created when we create the dice game. So we have the D1 and D2 objects here, and they are of type dice, and we name them in some good way. Often this refers back to the attribute or argument names that is actually used in the source code, so that we can easily trace between the source code and the sequence diagram. So we have D1 here and D2. We show the actual implementation by showing that the dice game object called G is involved, and the first thing that happens is that it sends a message roll to the D1 object, and this is implemented in this line. And then it sends the message roll to the D2 dice object, and that's this line. And then it gets the value from the first dice and gets the value from the second dice. So it's quite detailed in this case and shows more or less the exact implementation. Looking at the class diagram, we can of course see that we have the classes. So, all right, we have a dice class. We can then use dice objects in our sequence diagram. We know that we have this roll operation in the dice, so we can send messages from something into the different dice objects, the roll message. We also know that the dice game, as it has a relationship with dice, the dice game itself can be the one that sends messages to the dice. In this case, we know that the player does not have a relationship to the dice, so we cannot have messages in the sequence diagram from the player object to dice objects, because there is no way for player to know about the dice. However, we know that the player can send a message to the dice game object because we have this relationship between the player and the dice game. So this way you can know that if we have a message going from an object to another object of a different type, there must be a relationship between the classes in the class diagram. And this is a good way to test that you have not missed anything in your class diagram, or know that, okay, in order to fulfill this scenario shown by the sequence diagram, we need to have these relationships between the classes, because the objects sends messages over these relationships. To further detail, we have the message have fun, and it sends an object of type dice game to the player, and the player inside of this operation can then use this dice game object to send the message play to it. We can also show quite detailed the execution path of this if statement using this frame alt frame that shows what should happen if we have a win or what should happen if we don't have a win. And there are different types of frames for loops and such things also. Next, we will talk a little bit about yet another object model. And in this case, we have not seen it before, and it's quite an important diagram to know about. And maybe you have even done these types of diagrams before, but intuitively, so to speak. So an object diagram shows a static view over the executing system at a particular point in time. So it shows a snapshot of the state of the objects and their links. So when we started the have fun scenario for the dice game, we already had the objects created. So we had a player object created, and it has a link to the dice game object, and the dice game object in turn has linked to the dice and the first dice and the second dice. So this is the state of the system in regards to what objects there are and the relationships, the connections between these objects. So the player has a link to game, and game has a link to two dice objects. It's a snapshot of how the system looks. So the objects are of course an instance of a class, as we've seen before, and the link is an instance of a relation. So this link between the player and the game is an instance of the dependency relationship between the player and the game in the class diagram. And conversely, the links between the game and the dice and the game and the second dice is the instances of the associations that we could see in the class diagram or in the implementations as the attributes. And we can use the object model to be a starting point or an end point of a sequence diagram. So it's when we start the sequence diagram, we know that, okay, the objects look like this, and the sequence diagram happens, and then the object structure has changed in some way. Something has happened to the objects after this scenario has executed. And this enables us to understand how the objects actually look in particular situations. And this can be really good for debugging and understanding of root causes of problems that can happen. So you compare, okay, this is how it should look like. I use my debugger, and then I can see, okay, this looks strange compared to how it should be. In the dice game example, nothing really funny happens about with the objects. So we will take a look at some other example. A linked list is a data structure where each object points to the next object in the list. The first object in the list is often called the head. And insertions at the start of the list is very fast and takes constant time compared to, for example, an array of objects where you need to deallocate stuff and copy stuff for every insert you make. So looking at the class diagram, it could look something like this. So you have the linked list class. It contains a node, and we call this node head because it's the first node in the list. Then subsequently, each node can point to the next node in this list using this association relationship here. For simplicity, we just say that the nodes contain some kind of text string, and we have two operations in the linked list. We can insert something, and then it will be inserted first in the list of nodes, and we can print the list. So let's take a look at a simple scenario. We would like to print the text hello world using our linked list class. So in this case, we first need to insert the text world, and then we insert the text hello, because everything is added at the beginning of the list. So when we print the head first, and then the subsequent nodes that follow on that. So looking at an object diagram, we first have an empty list. So we just have the linked list object. So this is the class diagram you see here. So from this class diagram, we can create different configurations of objects if you would, you can view it in that way. So first we just have the linked list, and head points to nothing. So we just have this object. So when we insert the text world, we create a new node object, and we set the head to point to this object. So we still have our linked list object, but we create a new object and we call this object N1. And the text for this node object should be world, and head points to this new object. In the third step, we now want to insert the text hello. So head should now point to this newly created node with the text hello, and the hello's next link should point to the old head node with the text world. So the object diagram looks something like this. We have the linked list object, we have this new head object N2 with the text hello, and we have the old head object N1 with the text world. And N2 points to this old object N1 with its next pointer. And N1's next pointer points to nothing. So we have three different object diagrams that shows how the instances of the class diagram look in three different situations. First, we have the empty list. Then we have the list with one node in it, so the head points to one object. And then thirdly, we have a list with two nodes in it. And the new node becomes the head and points to the old head node. This prompts us to the first exercise. So create a sequence diagram for the previous scenario. So we start with the empty list and we end with a list with two nodes in it. What is the sequence of messages that are sent in this case? Second, we implement this. We put the classes in a package called LL for linked list. And the main function should create the linked list object and then execute the scenario. So first you create the linked list object and then you insert world and then you insert hello. Finally, you should print and we should see hello world in the terminal. While linked list could be fun, circular doubly linked lists are even more fun. So in this case, each node points to both the previous and the next node. So a node has this next pointer as before, and it also has a new previous pointer. So we can know that from a node we can step forward in the list and we can step backward in the list. And we have the list class again with the head pointing to the first node in the list. And this makes it easier to add nodes anywhere in the list, even at the last node. And we don't need to have a separate reference to the last node in the list class. We have two operations. We can add things first and we can add things last. And we can, of course, print. And this prompts us for the second exercise. So we have this little scenario where we add the text see Doubly last, and then the text hello first, and then the text world last. Create some object diagrams for this. So you have the empty one, and then you have three diagrams for the steps in the scenario. And finally, implement. You add the classes in their own package, and don't forget the print method. You could try some different text, but in the example here in the scenario, it should print hello see Doubly world. As a bonus, try to implement the circular doubly linked list without the use of null. And that's it for this video. I hope you have a better understanding of objects and classes and different types of models that we can use to understand a system better and help us implement and debug.